Hi guys, I am back again to try and explain rate laws a little bit and what a rate law is and how to find a rate law. So there's been a little bit of confusion, but a rate law is essentially how quickly a reactant is consumed in a chemical reaction. So let's say, for example, we have the reaction 2NO plus, let me grab my sheet, Cl2 yields 2NoCl. Okay, and these are all gaseous. Now remember, we can only do a rate law for aqueous and gaseous reactants, and it's only for the reactants. So I know that my rate law is going to be the rate equals K. Now K is called a reaction constant or a rate constant. It's just almost like the y-intercept in the equation. It's just a constant to kind of get the concentrations into rates. So I have K times the concentration of NO raised to some rate order. We don't know what it is yet, but experimentally we're going to have to calculate that. And then times Cl2 to some other rate order. Now we're going to use M because O looks like 0, and we don't know if it's a 0 order rate order yet. So here's our rate law equation. This is the rate law. So we need to look at some experimental data. So I have some data here. We have 3 trials. Let me quickly write this down. And rates. So for trial 1, I have 0.1 molar here, so that looks like 11, 0.1 molar here, 0.1, 0.18. And I have 0.1 here, 0.2, 0.36, and 0.2, 0.2, 1.45. Okay, so there's 3 trials, 3 runs. And in each different trial, they changed concentrations and they measured the rate. So between trial 1 and trial 2, all they did was double the concentration of Cl and see what happened to the rate. Whereas between trials 1 and 3, or I'm sorry, between trials 2 and 3, they doubled the concentration of NO. See where Cl is the same? They doubled the concentration of NO and tried to see what it would do to the rate. Okay, so in order to calculate our N, or our M, our rate orders, we need to take a look and see how the concentration affected the rate. In order to do that, we need to hold one of the 2 constant, which means we need to hold either NO constant or Cl constant. So we'll start with NO. So we're looking for a trial, or we're looking for 2 trials, where Cl concentration is held constant, and the NO concentration changes. Alright, that would be between trials 2 and 3. Do you see between trials 2 and 3, my Cl concentration remains constant, but my NO concentration doubles? So, in trial 2, my NO concentration is 0.2. I'm sorry, in trial 3, my NO concentration is 0.2. And in trial 2, it's 0.1. That's an increase of 2-fold. Okay? 0.2 over 0.1. But now we need to look at the rate. The rate in trial 3 was 1.45. Oops, that's a horrible 5. And the rate in trial 2 was 0.36. If I divide those 2 numbers, I'm going to see that that's pretty much a quadrupling of the rate. That's a quadrupling of the rate. So, since the NO concentration doubles, but the rate quadruples, I know that in respect to NO, it's a second order. Okay, it's a second order. In a second order rate reaction, the concentration doubles, but the rate quadruples. It's like squaring it. 2 squared is 4. So the change is squared. Okay? So, let me grab my eraser here. That's NO. Let's look at Cl2. So we're looking for a trial where the Cl concentration doubles, but the NO concentration remains constant. Because remember, when we do this, one has to stay constant. Right? We can only look at one thing at a time. Okay? So between trials 1 and 2, Cl doubles, but NO stays the same. So NO is not affecting our results. So if I look, the concentration of Cl goes from 0.2 to 0.1, or vice versa. That's a doubling of my concentration. And if I look at the rate, it goes from 0.36 and 0.18. And that's also a doubling. So if my concentration doubles, my rate doubles. Or, that's a first order rate reaction. It's a first order rate reaction. Because if I were to take 2, if I were to take my concentration and raise it to the first power, it would be 2. Okay, so now, let me erase this data table because we're done with that. Almost done with that. I'm going to keep that one tiny rate right there. Probably should have kept all of trial 1, but that's fine. Let me rewrite it. Luckily, it was pretty easy to remember. Okay, so now we have our rate orders, but we still don't have our K value. We still don't have our K value, our constant. Well, we're just going to pick a trial, and we're just going to plug numbers into it. So, here's my equation, and here's my data. So, rate is 0.18 equals K times the concentration of NO, which is 0.1, squared, times the concentration of Cl2, which is also 0.1, raised to the 1 power. And when we raise things to the 1 power, it just is what it is. Okay? So I'm going to do a little bit of math here. 0.18 equals K. That's 0.01 times 0.1. That's K, 0.001. Okay, so that's a horrible 8. Divide both sides by 0.001. And K should equal 1800. Okay, K will equal 1800. Okay, so this is mathematically how we calculate rate loss. Now notice K right now is unitless. We're going to get into the units of K at a later time. So hopefully this was a little bit easier to understand. Hopefully it cleared it up a little bit better. And have a wonderful day and good luck.